speak about complete Calabi-Yau metrics. So this is a problem that I learned about from Yau when I was a postdoc with him at Harvard, and something that I've been thinking about ever since. So let me begin by recalling, of course, any talk about Calabi-Yau metrics has to begin with Yau's solution of the Calabi conjecture. So if you have a compact Kähler manifold with, and I'm going to assume a stronger version of Calabi-Yau, so trivial canonical bundle. So then of course, Yau's theorem tells you that there exists a unique Kähler metric in the cohomology class of your fixed Kähler form, which solves the complex Monge-Ampere equation. So let me use red. So this is the complex Monge-Ampere equation, and this, of course, implies in particular that the associated Riemannian structure is Ricci flat. So following Yau's solution of the Calabi conjecture, there were two very natural questions that came up. So the first was whether there's a non-compact version of Yau's theorem. So that was in fact already proposed essentially in Yau's paper where he solved the Calabi conjecture, and he already began making progress on that problem. And the second question is whether there's a sort of natural geometric moduli space of Calabi-Yau varieties, and in particular, associated with this problem, there's an issue of understanding degenerations of compact Calabi-Yau manifolds, which has been an ongoing subject. So let me explain a little bit the difficulty of understanding question two, and actually, I also want to point out that these two questions are really kind of very closely related. So let's consider a polynomial. So PT, so this is a polynomial in n+1 complex variables, z0 up to zn, and it's homogeneous of degree n+1. So in particular, and t here is a complex parameter, which you can ignore for now. So p0 is a homogeneous polynomial of degree n+1, and p1 and p2 are two other holomorphic polynomials of homogeneous degrees d1 and d2, such that the sum is n+1. So as long as you make sort of generic choices, this polynomial will define for you a smooth hypersurface in CPN, which has trivial canonical bundle. So one can then ask what happens. So by Yau's theorem, so let's fix, I don't know, the class O1, the first term class of O1 is our background Kähler class. So then Yau's theorem tells you that there exists a Calabi-Yau metric on these varieties. But what happens, so as t goes to 0, so this is a family, and you can send t to 0. So you have some sort of nice, okay, so sort of schematically, some nice smooth Calabi-Yau manifold. And as t starts going to 0, so you start turning on this deformation, t goes to 0, something sort of odd starts happening, which I will draw again. Sort of schematically. Okay, so these are, of course, higher dimensional varieties, so this picture is nonsense. But in the end, you see that when t equals 0, then this thing factors as a product, and so this variety, at least at an algebraic level, seems to degenerate into two pieces, which are y1 and y2. So y1 is the 0 set of p1. y2 is the 0 set of p2. And they intersect along a divisor, which is D, which is the common 0 set of P1 and P2. Right, and Y1 and Y2 are themselves are not Calabi-Yau varieties anymore. So this is the sort of algebraic picture as T goes to 0. So one can ask what happens to the Calabi-Yau metrics on these PTs as T is going to 0. And the geometric behavior is going to be quite complicated. It's going to depend on sort of where you look and how closely you look. But one thing you can do is you can choose, for example, choose points xt in PT, in capital XT, I guess, where the curvature is maximal. The Riemann curvature of the Calabi-Yau metric is maximized. And then you can rescale around those points so that the curvature is 1, and then you can take a limit. So sort of zooming in around these points, you get a sequence, and it will converge in a very nice sense. So rescaling it and taking limits you obtain complete Calabi-Yau metrics, which will in general, which in this case will not have, they will be sort of collapsed. They will not have Euclidean volume growth. Okay, and the geometry of these complete Calabi-Yau metrics encodes in some sense the singularity formation and also the sort of geometric behavior of these Calabi-Yau metrics in a way that I'll try to explain a little bit later in the talk. So these you can view as some sort of bubbling. You can view these complete Calabi-Yaus as sort of bubbles in the singularity formation of these compact Calabi-Yau manifolds. Okay, so in particular, understanding the existence of these complete Calabi-Yau metrics is related to understanding the singularity formation in families of compact Calabi-Yaus. So how does one generate examples? Well, Yau has sort of explained to us what we should expect. So suppose you have a compact Kähler manifold with effective anticanonical bundle. So then you can take a section in this of this anticanonical bundle that has a 0 because we're assuming that Ky is not trivial, which is a codimension 1 complex subvariety. So in particular, divisor. Oops. And divisor. Okay, so then we can look on the complement of this set. So this is an open manifold now. But on the complement of the 0 set of this section sigma, we can invert it. And this gives us a holomorphic volume form with poles on D. And in particular, because it has a pole, this thing will not be integrable near D. So this sort of open Calabi-Yau manifold will have infinite volume. And so these are very good candidates for producing complete Calabi-Yau metrics. Now, in some sense, you can think of these examples as being algebraic because they're constructed out of this sort of algebraic information. So a pair, right? A pair of a compact Kähler manifold and an anticanonical divisor. So in fact, Yau conjectured that every complete non-compact Calabi-Yau manifold can be compactified by adding one of these divisors at infinity. So this is Yau's compactification conjecture, which is a major open problem. It's reasonably well understood in dimension 2 now, but outside of dimension 2, it's wide open. And he also proposed an existence problem, which is to answer the question of when do these examples that he's described, when do these examples actually admit complete Calabi-Yau metrics? So these are sort of two sides of the same coin, right? If you want to understand this compactification problem, you have to understand how, sort of in examples, how the geometry of the complete Calabi-Yau metric at infinity tells you what the compactification should be. So these two problems are really very closely related as well. Okay, so I want to focus on this existence problem. So the first result in this direction was sort of outlined in Yau's ICM address, and then appeared in work of Tian and Yau in 1990, which is the following situation. So suppose you have a Fano variety. So this just means that the anticanonical bundle is actually ample. And suppose you choose this divisor so it's actually smooth. So it's actually a smooth subvariety and reduced. So this sigma has only a simple 0. So then Tian and Yau proved that there exists a complete Calabi-Yau metric asymptotic to a certain explicit model near infinity, which is called the Calabi-Ansatz model. And this has lots of examples. So if you take CPN and you take again this smooth or this degree of n+1 homogeneous polynomial whose 0 set is smooth, then actually the complement of CPN has this complete Calabi-Yau, or complement of P equals 0 in CPN has this complete Calabi-Yau metric. So kind of interesting, it tells you that CPN, which is very much not Calabi-Yau, can be decomposed into two Calabi-Yau pieces. One is non-compact, right? CPN minus P equals 0, and P equals 0, which is also Calabi-Yau. So these metrics have very sort of interesting and bizarre behavior. So the volume growth is actually rational, not integral. So here's the volume growth so it's R to the 2n over n plus 1. And the tangent cone at infinity is the positive orthant. So these metrics are sort of collapsing to a one-dimensional base at infinity. Okay, and so these metrics actually are very important in describing the degeneration of, so for instance, K3 surfaces can collapse to a line. That's one behavior that can happen at the boundary of moduli space. And these metrics that Tian and Yau produced actually are exactly the pieces that you need to glue together to construct the K3 metrics near the boundary of moduli space. Okay, so that's sort of describing how these non-compact metrics can be used to understand the metric behavior of compact Calabi-Yaus. So in their paper, they asked the question of what happens when D is singular. So that's what I want to talk about. So the generic behavior is that D has simple normal crossings. So simple normal crossings just means that it's just a smooth subvarieties which intersect transversely. So locally it can be written as a zero set of a product of coordinate functions. Okay, so this is the generic condition. So generically, if you choose D, it will have this simple normal crossings behavior. So this problem has been sort of around since 1990, and there's sort of well understood in dimension 2, and outside of dimension 2, there was basically no progress. So a year and a half ago, so with in joint work with Yang Li, we solved this problem in dimension for the case of 2 divisors. So the theorem that we prove says if you have a Fano variety, so the dimension has to be bigger than or equal to 3. And suppose you have an anti-canonical divisor, which is 2 components with simple normal crossings. And then there's a sort of technical condition that these 2 divisors lie in this, or sort of in the same linear system up to tensoring. So L0 is fixed and DI are positive. So then there exists a complete Calabi-Yau metric on the complement of this divisor with two components. So again, this has lots of examples. So you take just a product of sort of generic product of 2 polynomials whose in CPN whose degrees add up to n+1. Then this admits a complete Calabi-Yau metric. And you can sort of view this as the sort of degeneration in some sense of the Tian-Yau metrics that I mentioned earlier, with the caveat that the asymptotic geometry is actually very different. So in this case, again, you have sort of odd volume growth, but differently odd. So 4 to the n over n+2 is the volume growth rate. And the tangent component at infinity in this case is now R2 rather than R. So it's the positive orthant in R2 rather than the positive sort of half line. So these metrics, so this is not rigorous yet, but the expectation is that these metrics should be very important in describing collapsing of Calabi-Yau manifolds, compact Calabi-Yau manifolds to higher dimensional base. Because roughly this tangent cone at infinity is describing the dimension of the base of the collapsing. So in this case, you would expect these metrics to be important in describing collapsing of Calabi-Yau threefolds to 2-dimensional real bases. Okay, and in fact, what we also described in this paper, a sort of inductive approach to the general case of simple normal crossings divisors, as long as the number of components is less than the dimension. So there's a condition here, and let me just remark that if you saturate this, so if the dimension is actually equal to the number of components, then there's some evidence that in fact, in this case, there may not exist a complete Calabi-Yau metric. Okay, we don't have definitive proof that that can't happen, but it certainly seems like there's some evidence. Okay, so let me explain a little bit the general strategy. How much time do I have left? Sorry. Okay. Well, I'll just go until you stop me. Sorry. Enough time. Okay. So let me explain the general strategy. So this goes back to the work of Yau and Tian-Yau. So the general strategy is that it suffices to find a model metric near this divisor D. So here in this picture, I've drawn D in blue, and there's some neighborhood of D, which is in red. And basically, as long as you can find a metric in this small neighborhood of D, you're in good shape, because Yau and Tian-Yau and Hein have produced a sort of general package which solves for you the Calabi-Yau equation of the complex modular pair equation outside of this set, as long as the asymptotics near D are sufficiently good. So you can view this as some sort of boundary value problem for the boundary value problem for the complex modular pair equation. You have a domain and sort of a target asymptotics outside of this domain, and you want to solve the complex modular pair equation with those asymptotics. So there's a very good way of doing this now, thanks to the work of Tianyao and Hein. So, so that reduces the problem to understanding what happens near D. So the idea is roughly speaking to use induction on dimension. So let me explain the picture a little bit. So let me just explain it in the case of 2 dimensions. So the local model here is you have 2 holomorphic coordinates, which cut out your divisors, D1 and D2. And the intersection of D1 and D2 is this intersection, which you should imagine goes back into the wall. So this is actually a compact, connected, smooth Calabi-Yau manifold, right? So Yau's theorem produces for you a Calabi-Yau metric on that compact manifold. So the holomorphic volume form has the following form. It's basically dz1 over z1, which dz2 over z2. Okay, now you have to allow me to lie a little bit at wedge omega y, which is, this is the sort of, okay, so in this picture I've drawn is basically a fibration, so which is not true globally, but let's just be tolerant for a moment. So omega y is the Calabi-Yau, is the holomorphic volume form on y. Okay, so you observe that that in fact D2 and D1 with their residue holomorphic volume forms, so these guys both satisfy the assumptions of the Tianyao theorem. Okay, so in fact there exist here omega ty complete Calabi-Yau metrics on defined on these hypersurfaces. And so the idea is that these should play some sort of the role of sort of boundary data for our problem in the generic neighborhood of y. So the idea is to look for Calabi-Yau metric, complete Calabi-Yau metric near y with asymptotics given by D1 and the Tianyao metric. Omega ty d1 di, so near di. So you have to, so these asymptotics have to be assumed in some singular fashion, right? Because this metric is supposed to be complete at D1 and D2, but the idea is that you should at least expect some sort of asymptotic expansion of your solution near D1 and D2, which it contains as this sort of leading order term in the metric behavior, the Tianyao metric. Okay, so that's the sort of rough idea. So this is, so if you can do this, right, then you get the following gluing picture. So now you have again, this same picture. So here you sort of have this metric with nice asymptotics. And then once you have this nice asymptotics, you can glue this to some sort of consistent extension of the Tianyao metrics near away from these points. So if you can do this with good enough asymptotics, then these things can all glue, and then you can use this as the model near infinity. So that's the sort of inductive strategy. Now, if you have 3 divisors, the same sort of thing holds. So you can look on D3, and each of these will fit the assumption of the 2 divisor case. So if you can solve the 2 divisor case, you can use that as sort of target asymptotics for the 3 divisor case, and then you can try to build the solution inductively on dimension, or inductively on the number of divisors. Okay, so this is the how to do this. So okay, so this doesn't really matter. There's some way of, which goes back to Yau, of reducing this problem to a real Monge-Ampère equation. Okay, so you want to solve the following real Monge-Ampère equation. So you're looking for a convex function now of real variables. So which satisfies, so u is a function of x1 up to xk. Each x corresponds to one of the divisors, which is convex. And it has this sort of increasing property. So d1, here, let me say d1 up to dk are just natural numbers, which you can imagine are given to you. And it solves this, this real Monge-Ampère equation. So the determinant of d squared u times this, this factor involving the gradient. Oops, sorry. Having a hard time. Okay. This factor involving the gradient is equal to 1. Okay, so as a sanity check, you can start with the example when k equals 1. So this should be the case of one divisor, which is the Tian-Yau case. You get an ODE. And that ODE has a solution, which is exactly this Calabi ansatz that appeared in the work of Tian and Yau. So there's an observation, which is that when k is bigger than 1, then this equation doesn't really make sense without some choice of boundary data. And that's where the inductive structure starts to play a role. So the boundary data here should be that, in fact, this prefactor, this gradient term, 1 up to k du by dxi di should go to 0 on the boundaries, on the boundary of the positive orthant, Rk positive. So when one of the variables goes to 0, then this gradient term should go to 0. And this is is not obvious. I'll explain where this comes from, but right. So this solution is defined on the positive orthant. Right. So okay. So this is what we did in the joint work with Lee, is we solved this problem. So when k equals 2 and n is bigger than k, then you can uniquely solve this real Majorana equation with asymptotics near di given by the Calabi ansatz. And this was really kind of a little bit of an experiment, right? Was to figure out what the right boundary data was so that the solution that you get out of this problem has these Tian-Yau or Calabi-Yau asymptotics near the boundary, right? So that was what we sort of figured out how to do in the case when k equals 2. So the two key ingredients were to determine this boundary data, which is consistent with the Calabi ansatz expansion, and the second key ingredient was to solve the equation with this boundary data. So it turns out that the boundary data is quite singular, right? As you can see in this Majorana pair equation, we're forcing this term to go to 0, so it's going to force the second derivatives of u to blow up. Okay, so that's what we did, and now some forthcoming work with Fried-Tong and Yau. We solved this equation in arbitrary dimension with arbitrary number of divisors, so we can prove that there exists a solution of this real Majorana pair equation in this positive orthant. And we can furthermore establish these Tian-Yau asymptotics near the hyperplanes. So now we're in Rk positive, so there are sort of several, the boundary is stratified. So you can imagine in R3 positive, the positive orthant in R3, there are 3 strata. There's the generic point, which is where one of the variables goes to 0. And when that happens, then we can establish exactly the asymptotics that we need. So these are are given by the Calabi ansatz. And so what remains is to understand the asymptotics near the corners where 2 variables go to 0. And in that case, we expect to have an expansion in terms of the solution that we produced in the work with Lee. So which is given explicitly in terms of some hypergeometric functions. But in this case, we don't have an explicit expression for this function. So we just know that it exists and has nice regularity properties, at least away from the edges. Okay, so the proof I won't describe, but it makes use of a lot of sort of Majorana pair type techniques. So the solution is actually constructed out of a min-max. So it turns out that this function can be viewed as a critical point of a functional which has a convex piece and a concave piece. And so we have to use min-max techniques to construct this function. And then addressing its regularity comes down to understanding the regularity of a function which solves an optimal transport problem, but where the sort of codomain of the optimal transport problem is actually undetermined. It's a free boundary equation. So it's an optimal transport with a free boundary, which is a sort of new feature that appears in this work. So I'll end just by again showing you this inductive picture. So you can view this, actually I like to view view the induction as starting with k equals 0. So if you're looking for a complete Calabi-Yau metric on X with a divisor D, where the divisor D has 0 components, so that's Yau's theorem, right? So Yau solved the case k equals 0. Also, the case k equals 1 appeared in Yau's work. So when you have k equals 2, then the k equals 1 and k equals 0 cases appear as the boundary data. So k equals 0 you can view as corresponding to this lower dimensional strata. K equals 1 are the edges. And we solve the equation with these asymptotics. And k equals 3, we've now solved this. In fact, for arbitrary k, we've now solved this equation with the right asymptotics near the highest dimensional strata. And so the problem now becomes understanding the asymptotics near the lower dimensional strata, but we're sort of optimistic that that's something that we can carry out. And then one can try to do this gluing picture and apply the Tian-Yau theorem to solve this problem for simple normal crossness divisors. Okay, I'll stop there. Thanks very much.